Hey everyone, welcome back. Today we're going to talk about safety, but we're going to do it through the lens of stability versus performance. So I want to make super clear that safety is the most important thing, and that's truly the entire purpose of this class, is we are integrating safety into senior design. You have a safety class, you have design classes, and this one's supposed to teach you about control so that you can implement safety into your designs. So in all the space of any type of controller that's available, we have everything. Kind of like the universe when we talk about systems and boundaries in thermodynamics. Here, every possible controller that could exist is basically the whole board. Imagine just this big blank canvas of every possible C or for controller. But there is a small subset or a box that is the space that are stabilizing based controllers. So these are types of controllers that actually would offer stability to your system, but they may not be very good. They're slow, they're lagging, they're just not very effective or efficient, but they'll stabilize, they'll do that job at least. And within the stabilizing controllers are ones that also offer performance objectives. And so of course, yeah, there might be a little box out here of like, they'll offer performance too, but they're not going to stabilize. Performance meaning that it gets you to a functional position and does so quickly, but it's not going to stabilize. You can think of that as like going off to infinity. It might do it quickly, but it's not going to actually be stable or safe. So we don't consider those out here. So we want to actually find these in the very center. What are going to be those types of controllers? And in order to find those performance-based controllers, we need to have ones that are fast response to changes. And so we might end up considering oscillatory-based responses. So we'll move into those in the future, like frequency-based and Bode plots. We want no excessive control actions or inverse responses. We really don't like inverse response. We try and avoid it. We want to make sure it has good proportional control. Remember, inverse response is that it first goes away and then goes back. Not really our desire. We need it to be insensitive to different model and measurement errors. So sensitivity is an important feature, but insensitive means it's not going to be making dramatic changes and then going off into the ether. We want it to be suitable over a wide range of operation conditions, meaning that it can be very well applied into many different scenarios. And that also considers safety. So in a wide range of operating conditions, that means as it's getting to a dangerous position, it can restabilize back as it should. So with safety being above all, we can actually tune the controllers to meet all of these objectives, especially 1 through 4, which will always need to be met for number 5. So to do this, we have online tuning, which is a data-driven model, and then we have offline tuning, which is model-based. So that means that this is actually based on data in our real system that we're collecting and measuring. And model-based is just simply, we have a model mathematically, we can exemplify from there and see what's going on. So one way to do this is through direct synthesis, and that'll be based on today's lecture. So let's move back into this system. Notice I've taken out the valve controller and I've also taken out the sensor controller, but we still have our standard feedback system here where we have our set point going in with this negative that has the controller. Then we have our process that goes into the additive of our DV, which has its own transfer function for the disturbance variable, leading to our controlled variable. That goes back and is able to move forward again. So in this, let's say that we're trying to find perfect or best optimal control. So our goal objective is to find CV over SP for a best situation. So we'll just call that like desired or D. That's our mission. That's what we want to do. I love smiley faces, so that's what we want. That's what we want to find. So to do that, let's build out what that would naturally look like on the forward approach. So based on per 4, we need to consider everything that's going on in the direct path. So that's GCGP over 1 plus, because of this negative system, and then everything in the loop, which is GCGP. So to identify where this might be optimal, let's try and solve directly for GCGP and then use that to solve for either GP or GC. So multiplying both sides, we're going to call this a singular term. Multiplying both sides by 1 plus GCGP, I get, by expanding and then I can move that to the other side and group them. So that would then become could divide that on both sides and get GCGP equals CV over SP over 1 minus CV over SP. So that means that we can actually then manipulate this to solve for either GC or GP. So let's go ahead and just solve for GC. That will be 1 over GP times CV over SP over 1 minus CV over SP. So if we're looking for the actual optimal condition here, our desired condition, then that's what we will get. But in the sense of when we're looking for this, that means we're looking for now when the process transfer function is essentially proportional to its own optimal condition, like this. So here, we're solving for the controller that will make this optimal. So let's consider a couple of possible conditions here. 1, if we want perfect control means that the output is always equal to the input. That means that our set function SP, or whatever that function might be for a set point, is allowing for directly equal to the output. Our set point is the desire for the output. The error is exactly 0 always every time. Therefore, if those are true, then dividing by SP on both sides, CV over SP would be 1 in that case. But for that to be true, that would mean that this is 1 over GP times 1 over 1 minus 1, which is 1 over 0, which approaches infinity. That would mean we need an infinite controller. And that's not very realizable, unfortunately. On the contrary, if you were to inverse back and solve for the GP, that would mean that the GP would need to be infinite when that's true. And that's also not realizable. So unfortunately, we can't actually solve for a perfect controller every time, unfortunately. Second condition is, let's see if we're solving for something with a potential time delay, like a first order transfer function. That would be GC that would allow for you to create for when the SP over CV is equal to 1 over TS plus 1. And that is definitely something that we can do. We know that in this case, my time here is going to actually be time of the closed loop specifically, and then we're going to get the speed of responsiveness for CV going to SP from this specifically. And that is realizable. That's something we can do, and that is a model that we can actually implement. The third of which, though, involves time delay that we need to consider. That's because, unfortunately, as we go from here to here, there is going to be some gap or delay in time in order for us to actually allow that to be realizable. We know that to be true from the previous lectures. Therefore, if we want some time delay, we can actually integrate this, because naturally this would be that e to the minus s function, where we can now integrate both of these together in order to generate a new model-based function, such as potentially we can use first order with time delay as k e to the s theta over ts plus 1. And that's something that we can absolutely do. And we can use that to try and solve out some potential problems here, where this would allow us to generate potentially what would this look like in our system. So we can try that. We can even do a second order, and we can see how this allows us to solve now for how the system will operate based on different functions. So this is just modeling different systems for how we're going to get there. Direct synthesis, we just plug in an example. We plug in an estimation for a model. This is definitely an offline model. This is data-driven models, and we'll move into more complex ones later. But for this one, we're going to start with the first order of time delay, and then we'll move into a second order of time delay and see what happens. Hey y'all, so let's try and do the first order model. In that, we're going to be assuming the process controller itself has this first order model. And we can use this directly in the expression that we've already analyzed. So before, we showed that GC is 1 over GP times CV over SP desired, 1 minus CV over SP desired. So now we're actually integrating this new first order model into our system to see how we can relate the controller of our system to the process of our system. So in this sense, we add that in directly. That is TS plus 1 over K e to the S theta times CV over SP. So in that way, we know that we're already going to use the first order model. That means that CV over SP is based on, as we said in the last one, our integration of them, which is going to just be e to the s theta over ts plus 1. So this involves our actual time delay and our first order. So that's because we have a realizable system. We're going to make this assumption to use this directly. So that means here, e to the minus s theta over ts plus 1 over 1 minus e to the minus s theta over ts plus 1. So now, what do we have here directly? Well, I can expand this ts plus 1 into this term directly, and if you notice, I have ts plus 1 over a ts plus 1 term, so those can cancel out. I also have an e to the minus s theta over e to the minus s theta that can cancel out, so I really just have 1 over k. So in that sense here, GC is equal to 1 over k times 1 over, now I have the ts plus 1 term to expand over here, ts plus 1 minus e to the minus s theta all over ts plus 1, which is ts plus 1 over k times 1 over ts plus 1 minus e to the minus s theta. And that's actually a term now that we can actually work with. So when we look at this, we still have this e to the minus s theta. So in the e to the minus s theta term though, remember, e to the minus s theta is approximately equal to 1 minus s theta from back when we were doing that analysis. And I'll move out of the way so that I'm not in the way here. So we can integrate that in to our system as ts plus 1 over k times 1 over ts plus 1 minus 1 minus s theta. So that's going to be minus 1 minus negative s theta, so plus s theta. So that means 1 plus 1 goes away. GC is ts plus 1 over k times 1 over ts plus s theta. We can extract the s out of there. We get ts plus 1 over ks t plus theta, just combining it together now. And now that's interesting. So in this sense, we actually do have this term that can be expanded a little bit further than this. And what I mean by that is, notice that directly we have two terms above. We have a ts over all that, and we have a 1 plus all of that. So we can pull this out into two expressional pieces. Here, we will have ts over ks t plus theta plus 1 over ks t plus theta. Those s's can cancel, and we get t over k times 1 over t plus theta. Plus, notice we have this 1 over s term here. I'm going to go ahead and extract the other piece first. So 1 over k times t plus theta times 1 over s. So we have a piece of this expression that is actually going to be related to nothing, and then 1 that's times 1 over s. But this is describing our controller. That's all we've done, is we've taken an optimal condition for CV over SP that integrates our first order system and a time delay, and we've taken a process of a model that exists that we can use, our first order process with time delay, but we've just put them back together to make GC. But what did we get? Well, remember back when we talked about PID control. We said that in PID control, Kc times 1 plus 1 over TIS plus TDS is, in reality, equal to GC, which if we expand that is Kc plus Kc over TIS plus Kc TDS. So that is GC and that is GC. So do we have any like terms? Is there anything we can extract from this? Well, first, let's think. In relating these terms together, which of these pieces have no s's? That's going to match for proportional. Which have 1 over s's? That'll be integral. And then what about the terms that have an s just in the standing in the numerator? Well, we don't have any. That would be our derivative control. So in this sense, we just built a controller with a first order system that has no derivative control. But we do have our Kc is T over K times 1 over T plus theta. And we can solve for our Ki or Ti from that as well, because Kc over Ti is equal to 1 over K T plus theta. And we know what Kc is directly. And so because of that, and knowing what these terms are, we can extract that out, and we, funny enough, find exactly that Ti is T. How wild. We just used a first order system to actually build that out. And that's exactly what we did. So some observations, we're saying proportional gain Kc is inversely proportional to K. That is true, because here, that's what we're seeing. Kc, and then our K of our process is down here. So we could have used Kp the entire time. I could just incorporate it at every step if we want to be absolutely sure. So Kp, 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 Kp. And yeah, so our Kc and our Kp are inversely proportional. And then we have time, of course, here, where this is the reset time from our integral controller. And that's going to be exactly equal to the natural time constant of the open loop process. The smaller Tc makes also, funny enough, for a larger Kc, because as this goes smaller, that goes bigger for the operating the same. So you get more response from your controller. And theta imposes a limit on Kc as well. As you can see here, that theta is involved directly with Kc, but does not involve with Ti. So really interesting to see some observations of that system. We can actually make some assumptions based off of that directly. So let's try out a second order model. Let's say that we had second order with time delay here, and that is going to be based off of this, but with a second time constant. So we would have Gp of S is K of our process, e to the minus s theta, over T1s plus 1 and T2s plus 1. As we rebuild out our controller, we still are going to use this exact same expression. So our controller will be 1 over Gp, which is the inverse, so T1s plus 1 times T2s plus 1, over Kp e to minus s theta, times Cv over Spd. That's still going to be this expression, but I'm going to add a C here to be related to the time constant on my controller. So I'm going to go ahead and say, why not e to the minus s theta over Tcs plus 1 over 1 minus e to minus s theta over Tcs plus 1. So e to the minus s theta here can cancel, but I can go ahead and multiply by Tcs plus 1 over Tcs plus 1. Now these two terms I'm going to go ahead and expand as well in the meantime. So this becomes, move out of the way, FOIL it, and then so that's T1 times T2 s squared plus T1s plus T2s plus 1 over Kp times that e to the s theta is already gone, and we're multiplying this directly across. So Tcs plus 1 over Tcs plus 1 is 1 over. This term is going to expand. So that's going to be Tcs plus 1 times 1 minus, that's going to cancel that term and leave us with e to minus s theta. As we just said before, e to minus s theta is approximately 1 minus s theta. So T1 T2s squared plus T1s plus T2s plus 1 over Kp times 1 over Tcs plus 1 minus 1 minus negative s theta is going to be plus s theta. We can go ahead and get rid of that. And notice that we just have an s term here. So we can go ahead and group some like terms. Gc is T1 T2 s squared plus T1 plus T2 times s. We just grouped these terms together, plus 1 over Kp times s times Tc plus theta. we can go and expand the numerator down into pieces, component pieces. And we're going to get, in this sense, let's go ahead and group these as perhaps T1 plus T2 times S over KP S TC plus theta plus 1 over KP S TC S plus, or just TC now, plus theta plus T1 T2 S squared over KP S TC plus theta. Now, why did I choose that order? Well, the S's here cancel, the S here does not cancel, and one of the S's here cancels. So that tries to match now this term that has no S's for the proportional, this term that has a 1 over S for my integral, and this term that has a numerator S for my denominator. Meaning, GC is T1 plus T2 over KP TC plus theta times 1 plus 1 over KP times TC plus theta times 1 over S plus T1 T2 over KP TC plus theta times S, where now this can help to build out my proportional term, my integral term, and my derivative term. And specifically in solving for these, we know that my proportional term Kc is all of this. Thus, we can say for a second order model system here, I'll just go and write it over here, Kc is T1 plus T2 over Kp Tc plus theta. And so if that's true, and my integral term is Kc over Tis, then I can expand those pieces out of there, and I'm left with my T1 plus T2 related to my Ti in particular, which in this case means that Ti is going to be T1 plus T2. I can also expand this in my derivative term here, where I have traditionally Kc times Td, where now my Td term is going to be T1 T2 over T1 plus T2, based on the math of going from KCTD equal to this expressional term. We can see the T1 T2 from there, and then the Kp of Tc plus theta expanded out, and that this is going to be true. But funny enough, while this system ends up modeling PI control, my second order system ends up modeling PID control, which is super interesting. When we think about that, the proportional control gain still depends inversely on my gain of my controller, and that's a pretty common feature in a lot of these direct synthesis kind of expansions. But as we think about this integral time, it's now equal to the sum of both of those pieces, the Ti plus T2. My derivative time is some quenched value of those, where it's this kind of like a geometric mean, if you will, like a triangular mean of those, which is definitely interesting because it has to involve around two competing poles, and that we need this derivative term in order to identify a second order process of that. So definitely really cool to see, and now the first order process really does end up looking like PI control. Second order is like a PID control, and higher order models are just going to get a lot more complicated in their structure. But we don't necessarily need to be more complicated always. We want something that's simple and fast. But if we need to, we can use actual computers to help us solve for a lot of this as well. And so through computation, we can go through a lot of those assumptions really quickly and identify dominant poles that will expand our system more clearly. And through the dominant pole that has to remain in the denominator versus being expanded to by time delay, we can build that out. Because as you might remember, this in theory could look like a second order but without time delay, and this could look like a third order without time delay, and so forth. So how do I take those terms and expand them in here, where my dominant ones are going to remain and allow the other ones to become my time delay? So hopefully this is interesting in this direct expansion, where you're just using this, you choose what you're going to expand on, and then you choose an exact model to process from there, build out your controller, and see how it operates. So hope you had fun, and I look forward to seeing you next time.